Now, let's explore Chapter 6, Architecting for Inference, the role of C# and modern.NET. Now, let's explore theoretical foundations. The theoretical foundation of containerizing AI agents and scaling inference pipelines rests on a fundamental shift in software architecture, the transition from monolithic, stateful applications to distributed, stateless microservices. In the context of cloud-native AI, this shift is not merely an operational convenience, it is a prerequisite for handling the computational intensity, variability, and scale of modern generative models. To understand this, we must dissect the interplay between containerization, orchestration, and the specific demands of AI workloads. Moving on to the microservice paradigm in AI, decomposing the monolith. Traditionally, an AI application might be a single executable. It loads a model, listens for requests, processes input, generates output, and logs results. This monolithic approach is brittle. If the model loading phase fails, the entire application crashes. If the model requires a specific GPU driver version incompatible with the logging library, the system is deadlocked. Microservices architecture addresses this by decomposing the application into single-purpose, loosely coupled services. In an AI context, this decomposition is logical and physical. Logical decomposition: 1. Ingestion service, handles input validation, sanitization, and perhaps preliminary tokenization. 2. Model service, the agent, the core compute unit. It loads the model weights, manages the inference engine, e.g., ONNX runtime, PyTorch, TensorFlow, and performs the actual tensor computations. 3. Post-processing service, handles output filtering, detokenization, or formatting. 4. Orchestration/workflow service, manages the state of a conversation or a complex multi-step task, calling other services as needed. Physical decomposition: this logical separation allows us to scale each component independently. The model service is typically the most resource-intensive, CPU/GPU bound, while the ingestion service is I/O bound. By separating them, we can scale the model service horizontally across multiple GPU nodes while keeping the ingestion service lightweight on standard CPU nodes. Analogy: the restaurant kitchen. Imagine a high-end restaurant, the monolith. One chef does everything, greets guests, takes orders, chops vegetables, sears the steak, plates the dish, and washes the dishes. If the chef is overwhelmed, the entire restaurant slows down. If the chef is sick, the restaurant closes. Now, imagine a modern kitchen, microservices. There is a receptionist, ingestion, a sous chef prepping ingredients, pre-processing, a line cook at the grill, model service, a saucier, post-processing, and an expediter, orchestration. Each is a specialist. If the grill station is overwhelmed, high inference load, you hire more line cooks, scale replicas, without needing to hire more receptionists. This is the essence of microservices, independent scaling of specialized units. Turning our attention to containerization, the unit of deployment. To deploy these microservices reliably, we need a standardized packaging format. This is where containers come in. A container bundles the code, runtime, system libraries, and system tools into a single artifact. In the context of AI, containerization solves the "it works on my machine" problem, which is exacerbated by the complex dependencies of AI frameworks. A model trained in PyTorch 2.0 with CUDA 11.8 requires a specific environment. Packaging this into a container ensures that the model service runs identically on a developer's laptop, with a GPU, a staging cluster, and a production cloud environment. The critical role of GPU pass-through: standard containers share the host kernel but isolate user space processes. To access GPUs, containers must be configured with specific runtime options, e.g., NVIDIA Container Toolkit. This allows the container to access the GPU device files and libraries on the host node. The container itself does not contain the GPU firmware, it contains the user space libraries, like libctn, that communicate with the host kernel drivers. Now, let's talk about Kubernetes, the brain of the operation. While containers provide the packaging, Kubernetes provides the orchestration, scheduling these containers onto physical nodes and managing their lifecycle. For AI workloads, Kubernetes is not just a scheduler, it is a resource manager. 1. GPU-aware scheduling. Kubernetes traditionally schedules based on CPU and RAM. AI workloads require GPUs. Kubernetes uses the concept of extended resources to manage hardware accelerators. Nodes expose their available GPU capacity, e.g., nvidia.com/GPU2. When a pod, the smallest deployable unit in Kubernetes, requests a GPU, the Kubernetes scheduler filters nodes that have that capacity available. Node affinity and taints. To ensure high-performance inference, we often use GPU nodes, equipped with high-end accelerators, and CPU nodes, for general compute. We can apply taints to GPU nodes, e.g., nvidia.com/GPU =true::no schedule, so that general workloads don't land on them. Then, we use tolerations in our model service pods to allow them to be scheduled on these tainted nodes. 2. The inference problem. Cold starts and batching. AI models are heavy. Loading a 70 billion parameter model into VRAM can take minutes. In a serverless or auto-scaling scenario, a cold start, spinning up a new container, introduces unacceptable latency. Theoretical mitigation, pre-warming, keeping a pool of warm containers ready to accept traffic. Model caching, sharing model weights across replicas using a distributed file system, e.g., S3, EFS, or a CSI driver like Rook/Ceph, rather than baking them into the container image. The container pulls weights on startup. Analogy, the toll booth highway. Imagine a highway, the Kubernetes cluster, with toll booths, pods. Cars, requests, arrive. If a toll booth is closed, pod crashed or scaled down, the car must wait for it to open, cold start. If the toll booth only accepts exact change, single request processing, throughput is low. Kubernetes acts as the traffic controller. It opens new toll booths, horizontal pod autoscaler, when traffic builds up. It directs cars to booths with the correct change lanes, GPU nodes. It closes booths when traffic subsides to save money, cost optimization. Now, let's explore scaling inference, the art of throughput versus latency. Scaling AI inference is non-trivial because it involves a trade-off between latency, time per request, and throughput, requests per second. 1. Horizontal scaling. Replicas. The most intuitive approach is to run multiple copies of the model service. If one replica can handle 10 requests/second, 10 replicas can handle 100. However, this is expensive. Each replica loads a full copy of the model into VRAM. If the model is 20 GB, 10 replicas consume 200 GB of VRAM. 2. Vertical scaling, resource allocation. Increasing the resources allocated to a single pod, e.g., requesting 2 GPUs instead of 1. This is limited by the physical hardware of a single node. 3. Autoscaling policies. Kubernetes uses the horizontal pod autoscaler, HPA, to scale replicas based on metrics. For AI, standard CPU metrics are often misleading because inference is heavily GPU bound. Custom metrics. We need to expose metrics like GPU utilization, VRAM usage, or inference queue depth, e.g., via Prometheus. The HPA uses these to make scaling decisions. CADA, Kubernetes event-driven autoscaling. A more advanced approach. CADA can scale based on external events, such as the length of a message queue, e.g., RabbitMQ, Kafka, containing inference requests. This decouples the arrival of requests from the processing, allowing the system to buffer load and scale proactively. Let's discuss optimizing model serving, quantization and batching. To maximize the efficiency of the hardware we scale, we must optimize the model itself and how it processes requests. 1. Quantization. This is the process of reducing the precision of the model's weights. A model trained in FP32, 32-bit floating point, uses 4 bytes per parameter. Converting to FP16, half precision, cuts memory usage in half. Quantizing to INT8, 8-bit integer, reduces it by a factor of 4. Why it matters for scaling. Smaller models fit into VRAM more easily. This allows us to run more replicas per GPU node or use smaller, cheaper GPU instances. It also speeds up computation, as moving less data is faster. The trade-off, lower precision can introduce numerical instability or slight degradation in output quality. However, for most LLMs, INT8 quantization has negligible impact on coherence. 2. Dynamic batching. In traditional web services, requests are processed one by one. In AI inference, the overhead of launching a GPU kernel for a single request is high relative to the computation time. The concept, instead of processing request A, then request B, we wait a few milliseconds to collect requests A, B, and C, we stack their input tensors into a single batch and process them simultaneously in one GPU kernel launch. The analogy, instead of a delivery truck making 3 separate trips for 3 packages to the same neighborhood, we wait for all 3 packages, load them into one truck, and make one trip. The fuel cost, GPU overhead, is roughly the same, but the throughput is tripled. Implementation. This is often handled by the inference server, e.g., NVIDIA Triton Inference Server, or the model runtime, e.g., ONNX Runtime Dynamic Batcher, sitting inside the container. Now, let's explore service mesh and inter-service communication. In a microservices architecture, services talk to each other. In an AI pipeline, the ingestion service talks to the model service, which might talk to a database service for context retrieval, RAG, retrieval augmented generation. The challenge is, 1. Security, traffic between services should be encrypted, MTLS. 2. Reliability, if the model service is slow, the ingestion service needs to handle timeouts gracefully. 3. Observability, understanding where a request failed in a chain of calls. The solution, service mesh, e.g., Istio, Linker to service mesh injects a lightweight proxy, sidecar, into every pod. This proxy intercepts all network traffic. Traffic management, it can implement retries, if the model service fails, try again automatically, and circuit breakers, if the model service fails 5 times in a row, stop sending traffic to it to prevent cascading failure. Security, the sidecar automatically upgrades HTTP traffic to HTTPS, MTLS, between services without the application code needing to handle certificates. Canary rollouts, this is critical for AI models. When deploying a new version of a model, e.g., upgrading from GPT 3.5 to GPT 4, or swapping a local model architecture, we don't want to switch all traffic instantly. A service mesh allows us to route 5% of traffic to the new version, the canary, and 95% to the old version. We monitor the canary for errors or performance degradation. If it passes, we gradually increase traffic. This is the safe deployment strategy. Now, let's explore observability, the eyes of the system. You cannot scale what you cannot measure. In AI microservices, standard logs are insufficient. 1. Metrics, we need to track latency, time to first token, TTFT, and total generation time. Throughput, requests per second, RPS. Resource utilization, GPU memory usage, GPU compute utilization. Business metrics, token count per request, error rates, e.g., model hallucination, flags. 2. Distributed tracing, using tools like OpenTelemetry, we can trace a request as it flows through the ingestion service-model service-database. If the model service is slow, the trace shows exactly where the time was spent, e.g., 200 milliseconds in queue, 500 milliseconds in inference, 50 milliseconds in post-processing. 3. Logging, structured logging, JSON, is essential. Logs should include a correlation _ID to link all events related to a single user request. Let's discuss architectural implications and C# integration. While the infrastructure is language agnostic, the application code, the microservices, must be written to leverage these capabilities. In C#, we use specific patterns to build cloud-native AI agents. Interfaces for abstraction, as mentioned in Book 6, interfaces are crucial for swapping between different AI providers or model architectures. In a microservice, the iModel service interface defines the contract for inference. We begin by importing the system, threading, tasks namespace. This is crucial because, in cloud-native applications, I/O operations like making network calls to an AI model or performing complex computations are inherently asynchronous. Using task and async/await allows our application to remain responsive and handle multiple requests concurrently without blocking threads. This is a fundamental pattern for building scalable, high-performance services, especially when dealing with external dependencies or long-running operations, which AI inference often entails. Here, we define the AI agent's core namespace. Namespaces are essential for organizing code, preventing naming collisions, and improving readability, especially in larger projects or when integrating multiple services. In a microservices architecture, each microservice might have its own core namespace, clearly delineating its responsibilities and boundaries. This particular namespace will house the fundamental abstractions for our AI agent's inference capabilities. At line 6, we declare the iInference service interface. This interface is a cornerstone of our architectural design, embodying the dependency inversion principle, DIP, from Solid. It defines a contract for any class that provides AI inference capabilities. Notice how we are abstracting the how of inference. This is critical for cloud-native applications. We don't want our consuming services to be tightly coupled to a specific AI model provider, e.g., OpenAI, a local ONNX runtime, or a custom Llama deployment. This loose coupling allows us to swap out inference implementations without modifying the consuming code, which is vital for flexibility, testing, and future-proofing in a rapidly evolving AI landscape. Look at line 10, where the generateAsync method is declared within our iInference service interface. This method takes an inference request and returns a task inference result. The task return type reinforces the asynchronous nature of AI inference, as discussed earlier. This design promotes non-blocking I/O, which is essential for maximizing throughput and minimizing latency in a cloud environment. Imagine if inference calls were synchronous. A single slow model response could block an entire thread, severely limiting the number of concurrent requests our service could handle. By making it async, we ensure that our service can continue processing other requests while waiting for the AI model to respond, a key characteristic of scalable microservices. At line 13, we define the inference request record. Records in C# are a concise way to declare immutable data structures, which are perfect for representing requests and responses in a stateless microservice architecture. An inference request encapsulates the input needed for an AI model, specifically a prompt, the text input for the AI, and max tokens, a common parameter controlling the length of the AI's response. Using immutable records like this contributes to thread safety and predictable behavior, as their state cannot be changed after creation. This is a best practice for data transfer objects, DTOs, in distributed systems, as it simplifies reasoning about data flow. Finally, at line 14, we define the inference result record. Similar to inference request, it's an immutable data structure designed to hold the output from our AI inference. It contains text, the generated textual response from the AI, and embeddings, a numerical representation of the input or output, often used for semantic search, similarity, or downstream AI tasks. Providing both text and embeddings in a single, well-defined record simplifies the contract for consumers and ensures that all relevant output from an inference call is consistently packaged. This structured approach to data exchange is vital for maintaining clarity and interoperability across different components of a microservice system. Dependency injection, DI, and lifetimes. In a containerized environment, managing the lifecycle of heavy objects, like the ONNX runtime session or a torch model, is critical. Singleton lifetime. The model loader should be registered as a singleton. Loading a model is expensive, we want to do it once per application lifetime, per container. Scoped lifetime, the inference context might be scoped to a single HTTP request. We begin by importing necessary namespaces. At line 1, Microsoft, extensions.dependency injection is crucial because it provides the core abstractions and implementations for dependency injection, DI, in ASP.NET Core. This framework is designed to build loosely coupled and testable applications. The startup class, starting at line 3, is a convention in ASP.NET Core where we configure application services and define the request processing pipeline. The configure services method, at line 5, is where we register our application services with the DI container. This method is called by the host before the application starts accepting requests. Notice how at lines 7 to 9, we register our ONNX model loader as a singleton for the iModel loader interface. This is a critical architectural decision, especially in a cloud-native context. The comment at line 8 highlights that the model is heavy. This implies a significant memory footprint or a time-consuming loading process. By registering it as a singleton, we ensure that the ONNX model loader instance, and thus the underlying ONNX model, is initialized only once when the application, or container, starts up. It then remains in memory and is reused across all subsequent requests to this particular container instance. This approach conserves memory, reduces startup latency for individual requests, and improves overall throughput, which is vital for efficient resource utilization in containerized environments. Following the iModel loader registration, at lines 11 to 14, we register ONNX inference service as a singleton for the iInference service interface. This choice is directly influenced by its dependency on the iModel loader, which we also registered as a singleton. Since the inference service will likely hold a reference to the loaded ONNX model, making it a singleton ensures that it, too, is instantiated once and shares the same model instance. This reinforces the memory efficiency and fast inference benefits. We emphasize that for stateless services like an inference engine, singleton is often the best choice, as it avoids unnecessary object creation and destruction overhead per request, contributing to better performance and scalability in a microservices architecture. Finally, at lines 16 to 17, we register inference controller as scoped for the IAPI controller interface. This is the standard practice for controllers in ASP.NET Core. A scoped lifetime means that a new instance of inference controller will be created once per client request, or scope. This ensures that any request-specific data or state managed by the controller is isolated to that particular request, preventing data contamination between concurrent requests. While the controller itself might be lightweight, its dependencies, like the iInference service, are injected, and their lifetimes are managed by the DI container. This separation of concerns and appropriate lifetime management are fundamental for building robust and scalable web APIs in a cloud environment. Resilience with Poly. when communicating between microservices, e.g., the ingestion service calling the model service, network transient failures happen. Poly is a .NET resilience library. Retry policy: if the model service times out, perhaps due to a cold start, Poly can retry the request with exponential backoff. Circuit breaker: if the model service is down, e.g., GPU node failure, Poly can open the circuit, failing fast immediately without waiting for timeouts, preserving resources in the calling service. We begin by importing necessary components from the Poly library. Poly is a resilience and transient fault handling library for .NET. It allows us to express policies like retry, circuit breaker, timeout, bulkhead isolation, and fallback in a fluent and thread-safe manner. Here, we specifically bring in Poly itself and Poly retry, indicating our intention to implement retry logic. This is a crucial cloud-native pattern, acknowledging that microservices and distributed systems are inherently unreliable due to network latency, temporary service unavailability, or transient errors. Without such policies, a temporary glitch could lead to cascading failures throughout our system, impacting user experience and system stability. At lines 5 to 12, we're defining an asynchronous retry policy using Poly. Notice we're creating an async retry policy, which is essential because most I/O operations in cloud-native applications, especially HTTP calls to other services, should be asynchronous to avoid blocking threads and improve scalability. We instruct this policy to handle HTTP request exception. This means any time an HTTP request exception occurs during the execution of the protected code, Poly will consider it a transient fault and initiate a retry. This is a common exception type when dealing with HTTP client errors, indicating issues like network connectivity problems, DNS resolution failures, or the target server being unreachable. By specifically handling this exception, we're targeting network-related transient faults, which are very common in distributed environments. Here, we configure the retry behavior. We specify retry count, 3, meaning the operation will be retried a maximum of 3 times after the initial failure. This number is a balance between resilience and not unduly delaying the overall operation or consuming excessive resources for a persistent failure. More importantly, we use sleep duration provider to implement an exponential backoff strategy, attempt equals time span. From seconds, math, pow, to attempt. This means the delay between retries will increase exponentially, 1 second, then 2 seconds, then 4 seconds, etc. This is a best practice in distributed systems. Why? Because retrying immediately and repeatedly can overwhelm an already struggling service, exacerbating the problem. Exponential backoff gives the downstream service time to recover, reducing contention and improving the chances of success on subsequent attempts. It's a fundamental pattern for graceful degradation and system stability. At lines 10 to 12, we define an onRetry action. This callback is executed each time a retry is initiated. Here, we simply log a message to the console, indicating which retry attempt it is and what exception triggered it. This logging is invaluable for observability in a cloud-native environment. When deployed to Kubernetes or any container orchestration platform, these logs would be collected by a centralized logging system, like ELK Stack or Grafana Loki. This allows us to monitor the health of our service and its dependencies, identify transient issues, and understand if our retry policies are being invoked frequently, which might signal deeper problems with a downstream service that require investigation beyond transient fault handling. Now, let's talk about theoretical foundations. The theoretical foundation of cloud-native AI is the decoupling of concerns. By breaking down a monolithic AI application into specialized microservices, ingestion, inference, post-processing, we gain the ability to scale each part independently. Containerization provides the standardized packaging to run these services anywhere. Kubernetes provides the orchestration logic to manage their lifecycle and resource consumption, GPUs. Finally, optimization techniques like quantization and dynamic batching, combined with service mesh observability, ensure that we can handle high-throughput, low-latency inference reliably. This architecture transforms AI from a static, brittle application into a dynamic, resilient, and scalable system. Now, let's talk about basic code example. Here is a simple, self-contained example demonstrating the core logic of a containerized AI agent that accepts a request, performs a mock inference, and returns a response. We begin by importing necessary .NET namespaces. Notice at lines 1 to 5, we're bringing in system 4 basic types, system, collections, generic for collections like dictionary, system, link for query operations, though not heavily used here, it's a common inclusion, system, text, JSON for JSON serialization/deserialization, and system, threading, tasks for asynchronous programming. These are foundational for building modern, responsive applications, especially in a cloud-native context where non-blocking I/O is crucial for efficiency. At line 7, we define our containerized AI agent namespace, which helps organize our code and prevent naming conflicts. Within this, at lines 9 to 14, we declare the inference request class. This class acts as a data transfer object, DTO, for incoming requests to our AI agent. It encapsulates the prompt, the input text for the AI model, and parameters, which could hold model-specific settings like temperature or top_k. This structured approach ensures clear communication contracts between services, which is a hallmark of microservices architecture. Following the request, at lines 16 to 22, we define the inference response class. This DTO represents the structured output from our AI agent. It includes the result, the AI's generated output, processing time ms to indicate how long the inference took, critical for performance monitoring and auto-scaling decisions in cloud environments, and timestamp for when the response was generated. This provides valuable telemetry, enabling us to observe the agent's performance and health, which is vital for operational visibility in containerized deployments. At lines 24 to 31, we introduce the inference service class, which is the heart of our AI agent's logic. This class is designed to encapsulate the actual AI model's interaction. The comment at line 24 highlights that in a real-world scenario, this service would integrate with specific ML frameworks like ONNX or TensorFlow.net. The process request async method, starting at line 30, is declared as async tasked inference response, indicating it's an asynchronous operation. This is a best practice for I/O bound or computationally intensive tasks like AI inference, preventing the blocking of the main thread and improving the overall responsiveness and throughput of the service. Inside process request async, at line 32, we start a stopwatch. This is a practical way to measure the execution time of our inference logic, aligning with the processing time ms field in our inference response. Then, at line 35, we introduce await task, delay, new random, next, 100, 500. This is a crucial simulation. It mimics the latency typically associated with AI model inference, which can involve complex computations or even network calls to a dedicated AI accelerator. Without this delay, our mock service would run too fast to demonstrate realistic performance characteristics. Lines 38 to 40 show a simple, mock AI logic, transforming the prompt to uppercase. This placeholder would be replaced by actual model prediction code. After the simulated processing, at line 42, we stop the stopwatch. This captures the total time taken for the mock inference. Then, at lines 44 to 49, we construct and return a new inference response object. We populate its result with our process string, set processing time ms using the stopwatch.elapse milliseconds value, and record the timestamp as datetime.utc_now. Using UTC is a standard practice in distributed systems to avoid time zone issues, ensuring consistency across different services and regions in a cloud environment. At lines 52 to 61, we define the program class, which serves as the entry point for our console application. The main method, starting at line 57, is declared as public static async task main, string, args. The async keyword here is essential because our application will perform asynchronous operations, such as simulating network requests and delays. Lines 59 to 60 print informative messages to the console, indicating that the agent is starting and listening on a specific port. This is helpful for debugging and for understanding the application's state, especially when running inside a container where logs are the primary means of observation. At line 62, we instantiate our inference service. Notice that we're creating a new instance directly. In a real ASP.NET Core application, this would typically be managed by a dependency injection, DI, container, often configured as a singleton if the AI model itself is large and expensive to load, to optimize memory usage and startup time within a container. The comment at lines 64 to 66 explains that this while true loop is a simplification. In a production ASP.NET Core app, the web server, Kestrel, and its middleware pipeline would handle incoming HTTP requests and dispatch them to controllers, making this explicit loop unnecessary. Here, it simulates the continuous processing nature of a microservice. The while true loop, starting at line 68, represents the continuous operation of our microservice, constantly waiting for and processing requests. Inside the try block, at lines 71 to 77, we simulate receiving an incoming request. We create a mock request with a sample prompt "Hello Kubernetes" and some parameters. This mock request stands in for an actual HTTP post body that would be deserialized from JSON. The comment at line 71 is significant. In a cloud-native setup, a service mesh like Envoy or an API gateway would typically handle routing and potentially even some request transformation before it reaches our agent, abstracting away the low-level networking details. At line 79, we serialize the mock request to JSON and print it to the console. This simulates logging the incoming request, which is a crucial practice for debugging, auditing, and monitoring microservices in production. Then, at line 81, we await inference service.processRequestAsync, mock request. The await keyword is vital here. It allows the program to perform other tasks while the processRequestAsync method, which includes an artificial delay, is executing, demonstrating non-blocking I/O. Finally, at line 84, we serialize and print the response, simulating sending back an HTTP 200 OK response with the inference result. This output provides immediate feedback on the agent's processing. At line 87, we introduce a wait task, delay, 5000. This 5-second delay simulates an interval between processing requests, or perhaps a periodic health check. In a real-world scenario, continuous requests would arrive, but this delay helps illustrate the discrete nature of processing. The catch block, starting at line 89, is crucial for resilience. It catches any exceptions that occur during the simulated request processing. The comment at line 92 highlights a key cloud-native concept. If an agent consistently throws errors, health checks, e.g., Kubernetes liveness probes, would fail, leading to the container being restarted or replaced, ensuring system stability and self-healing capabilities. Thank you for your attention. This lesson is excerpted from Volume 7, Chapter 6 of the C# and AI Masterclass ebook series and from the volume Cloud-Native AI and Microservices, Containerizing Agents and Scaling Inference. You can find all the details here, https://github.com/edgarmilvas/C# programming series. The ebook also includes diagrams, advanced examples, and 5 exercises with solutions for every chapter. There are 26 chapters. If printed, it would exceed 600 pages. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.